Okay, scale factors and conversions. These are pretty easy, but there's something that everyone gets wrong, so let's get to work and figure it out. Okay, question 1. Figure 1 is a square with the side length x. Figure 2 is a square with the side length of 3x. What is the ratio of the area of figure 1 to the area of figure 2. Okay, so you have figure 1 and figure 2. Although you don't have numbers, you know figure 1 is length times width, or x squared. Figure 2 is length times width, or 3x times 3x, which is 9x squared. So the ratio of figure 1 area to figure 2 area is 1 to 9. So I know people are like, oh, it should be 1 to 3, right? Because this is 3 times bigger, but the area is 9 times bigger. Why? Because it's not just length, it's length times width. Pretty simple, we're good. Okay, question 2. Figure 1 is a square with the side length of x. Figure 2 is a square with the side length of 3x, so a lot like question 1. What is the ratio of the perimeter of figure 1 to the perimeter of figure 2? And you're like, last question, the area was length times width, and that was important. So here, perimeter, and the perimeter is 4 times the side length, so maybe the number 4 has something to do with it, and maybe the answer is actually 4 times 3, or 1 to 12. But that's a twist. It doesn't really matter. Because think about it. So you have figure 1, perimeter of figure 1 is 4x, right? Figure 2, perimeter of figure 2 is 3, 3, 3, 3, 12x. But that's just, you know, you multiplied both of them by 4, so you can divide both of them by 4 and get 1 to 3. So 1 to 3. We're good. Okay, question 3. This is the one people miss. Figure 1 is a cube with the side length of x. Figure 2 is a cube with the side length of 3x. What is the ratio of volume of figure 1 to the volume of figure 2? Alright, your figure 1 volume is x cubed. Figure 2, the volume is 3x times 3x times 3x, or 27x cubed. So because we did questions 1 and questions 2, hopefully you're like, oh, this is pretty simple. And you know what it is. If you just take the length times width times height, you'll know that it's 3 times 3 times 3, and you'll have a pretty easy time getting 1 to 27. We're good. Okay, question 4, a lot like question 3. Figure 1 is a cube with the side length of x. Figure 2 is a cube with the side length of 3x. What is the ratio of surface area? That's the key term here. Figure 1 to the surface area of figure 2. And you know, surface area is just one face of a cube times 6, right? Because the cube has 6 faces. So this is x and x. So the surface area of one of those sides is x squared. You got 6 of them. So figure 1 is 6x squared. Figure 2, this is 3x by 3x. So each face is 9x squared. 9x squared times 6, because there are 6 faces, is 54x squared. That's figure 2. We're talking about surface area here. And look, we multiplied each by 6, so we can divide each by 6. And we can divide them by 6x squared, in fact, and we get 1 over 9. And you think about it, well, that's a lot like the area. Yeah, it was a lot like the area. Same basic rules apply. We're good. Okay, those area questions that we just did are kind of a lead up to this question, because this is another question that people get wrong all the time. A map includes a square preservation area with a side length of 4 inches. Okay, so you have a map. That's a picture of a map, you know, land area. Square preservation area inside the map. And it's 4 inches by 4 inches. Nice of them to have a preservation area. The scale is 2 miles for every 1 inch. Okay, so let's do miles per inch, and we have 2 miles per 0.5 inches, and this guy here is 4 inches by 4 inches. So we're gonna say 4 inches. How many square miles is the preservation area? And you're like, okay, I know how to do this. I know how to do math. I know 0.5 times 8 gets me to 4. So 2 times 8 will get me to 16. And I'm like, all right, 16 is my answer. But no, 16 is not your answer. 16 is totally not your answer. It's totally wrong. And it's there as a distractor to try to trick you. It means this side is 16 miles and this side is 16 miles. But the question says how many square miles. It doesn't say how many miles is the length of the preservation area. It says square miles. So you got to make sure that you don't forget to stop. You don't forget to do part 2 after you do part 1. You find each length is 16. Now you got to multiply 16 by 16, and if you do that, you'll get 256, and that's the answer. We're good to go. Okay, question 6. A blueprint includes a square pool with the side length of 5 inches. Nice of them to have a pool. No pools are really square. They're always rectangular or other shapes, but it's kind of weird. Anyway, let's just keep going. The scale is 2 feet for every 1/2 inch. Okay, so we have another, question here. Curiously like the first one, right? So your scale is 2 feet per 0.5 inches, and you have 5 inches here and 5 inches here. How many square feet is the pool? So you're like, oh, I know how to do this. We just talked about this before. How do you go from 0.5 to 5? You multiply by 10, so you're going to multiply the numerator by 10 as well. You're going to get 20. You're going to have a 20-foot pool by a 20-foot pool. So how many square feet is the pool? It's not 20. It's not 200. It is 400. And we're good. Okay, question 7. And I know, just looking at question 7, I know what you're thinking. You're thinking scientific notation, ugh, I hate this stuff. And I agree with you. Scientific notation is dumb. Scientists don't talk like this. Scientists would never say that the Earth to the Sun is 9.3 times 10 to the 7th miles. Scientists would just not say this. Scientists would say it's 93 million miles. That's what they would say. Nobody ever uses scientific notation in the science world. They just throw the numbers into a spreadsheet and they're happy. So scientific notation is dumb. However, it is a good tool to kind of combine concepts and make sure that you really understand place value and multiplication and exponents. So I understand why it's on these tests. I understand why whoever, wrote the Common Core put it in the 8th grade Common Core standards. We do have to deal with it, so let's just get through it. How many grams is in 670 kilograms? Well, a kilogram, or you should, and I'm not going to go through every single conversion that there ever was or ever will be, but a kilogram, equals 1,000 grams. So you should know this. You should know kilo means 1,000. Like I said, I'm not going to go through every conversion that there ever was or ever will be, but you should know kilo means 1,000. Okay, so how many grams? You have grams in 670 kilograms. Well, if you have 670 kilograms, that 1 times 670 will get you there, right? So we're going to multiply this by 670 as well, and you get 670,000. And you're like, okay, well, how do I convert that into scientific notation? Well, remember, this number here, the exponent, is not the number of zeros, it's the number of places that you jump, right? So this is 1 jump, 2 jumps, 3 jumps, 4 jumps, 5 jumps. Remember, it's 5 jumps, 4 zeros and 5 jumps, because you got to get to 6.7, because your first term in your scientific notation has to be between 1 and 10. It has to be, digit, decimal point, and then other stuff. So there we go. All right, so 5 jumps means we have to the 5th power, which means 6.7 times 10 to the 5th is our answer. And we're good to go. Question 8, because question 7 was so much fun, let's do question 8. Okay, kilograms per grams, and we know that there are 1,000 grams in 1 kilogram because we know kilo means 1,000. Okay, so how many grams do we have? We have 0.023. And how many kilograms is that? Okay, well, you're like, we just got to cross multiply and divide, right? So what we're doing is, you can think about it as cross multiplying and dividing. Yeah, that's how I'd probably do it. I'd be like, okay, 1 times 0.023 is 0.023, and then you're going to divide by 1,000. When you divide by 1,000, you're going to move that decimal point 3 places to the left, right? So just think about it as cross multiplying and dividing. If you divide by 1,000, it gets a lot smaller. It gets 3 decimal places smaller. So you have 0, 2, 3, and you got to move that decimal point 1, 2, 3 more places because you divided by 1,000. Okay? We're good to go. Now we got to convert this to scientific notation because math questions have 2 steps sometimes. And how many decimal places do we have to jump in order to get the decimal point there, right? Because we're not counting zeros, we're counting decimal places. So we have 1, 2, 3, 4 zeros, and then another jump. So we have 5 spaces we have to move. We're a number less than 1. It's not a negative number, it's a number less than 1, so we're dealing with negative exponents in our scientific notation. 5 decimal places means it's 2.3 times 10 to the negative 5th. And we're good. Question 9, how many milliliters in 5,400 liters? Okay, milliliters. Not going to go through every conversion that has ever existed, but you should know milli means 1,000, like millennium. Okay, so we have milliliters per liters. We have 1,000 milliliters per 1 liter. It doesn't really matter what's in the numerator or the denominator. The relationship's what is what it's important. 5,400 here. Oh, so what do we have to do? 1 times 5,400 gets us 5,400. So we have to multiply this number by 5,400 and we get 3 more zeros. And we're like, okay, that's cool. We have 5,400,000 milliliters. So what is that in scientific notation? Well, how many decimal places do I have to go? I have to go 3, 6, right? 1, 2, 3, 4, 5, 5 zeros, and then 6 decimal places to get to 5.4. We're good. Okay, on to question 10. How many liters in that number of milliliters? And remember, milli means 1,000. You just got to know it. I'm not going to go through every one of the conversions, but I mean milliliters. Come on, you should know this. Okay, milliliters per liters. You have 1,000 milliliters in a liter. And you have this number of milliliters, 0.12317. So again, I would think of this as cross multiplying and dividing. You cross multiply, you divide. When you divide something by 1,000, it gets even smaller, so the decimal point is going to have to go that way. How many places? Well, you have 3 zeros here, so it's going to go that way 3 places. And you're going to get 1, 2, 3 more zeros, then 1, 2, 3, and then 17. All right, so how do you put this number in scientific notations? Count the number of decimal places, not just the number of zeros, right? So you have 1, 2, 3, 4, 5, 6 zeros, and then you have 7 to get to 1.7. So you have to go 7 places, you know? 1, 2, 3, 4, 5, 6, 7 places. So your answer is A. And we're good.